Good afternoon. Thank you everybody for attending. I'm Cory Southall, and today I'll be presenting the findings from my capstone study, which was object detection using deep learning in ArcGIS Pro. So before we get started, I think it's important to provide a little context on what deep learning is. Deep learning uses artificial neural networks to learn data and try to make decisions the same way the human brain would. These artificial neural networks are multi-layered connected networks. And I'll try and explain this a little bit more in a minute. You can see an image of it on the top right. We'll be talking about deep learning through the computer vision lens, so I'll try and explain it in that way. So the artificial neural networks most used for computer vision are known as convolutional. These convolutional neural networks take an image, as you can see in the bottom left, and it breaks it down through a series of layers and assigns weights to these images to help identify different objects in them. We analyzed two convolutional neural networks in the study, ResNet 34 and ResNet 50. The number behind there just refers to the number of layers in each one. And these were trained and run through a single shot detector. You can see an image of it in the bottom right. These use a bounding box structure, and it uses grids to break down the image, and then bounding boxes to notate where the objects are. So why does all this matter? I think all of you have heard about Tesla and what they're doing with the autonomous vehicles that can drive themselves. Computer vision is the main technology behind this. The computer vision segments the video that's coming in, as you can see in the bottom right, and it breaks down these images and allows the computers to make decisions. And this applies to a lot of different areas as well. It can be applied to medical imaging to help detect different problems on medical scans, such as cancer and pneumonia. The objectives of the study were pretty simple. We wanted to detect vehicles using Esri's ArcGIS Pro and their tool set using the deep convolutional neural networks. We wanted to assess the two convolutional neural networks that I mentioned earlier, ResNet 34 and ResNet 50, to see which one had the best predictive performance. We also wanted to see how complex it would be to train these and run these using Esri's ArcGIS Pro toolset. Because one of the main problems with deep learning is the complexity behind it, because it takes an advanced knowledge of deep learning and also of programming. So Tucson, downtown Tucson, actually proved to be a perfect study area for the capstone study, due to the high volume of vehicle traffic, which I'm sure most of you know about. The area in brown on the map notate where the training tiles were collected from, and the area in green notates the final test area. I did my best to collect a mix of residential and commercial real estate to test the full capabilities of the model over all environments to see how well it could detect vehicles. 6-inch resolution imagery was collected from the PIMA Association of Governments from 2015 for the study. The first step of the process was to prepare the software, because the Python libraries that were necessary for deep learning weren't pre-installed into ArcGIS Pro. So to accomplish this, I used Anaconda, which is a data science program, to download all of the necessary libraries that you see on the screen. Anaconda also housed the integrated development environment, which we used to run the code, which was Jupyter. Jupyter Notebooks actually allows you to segment the code and run it all individually, which really helped out with the process. The next step was to develop and export the training samples. It was really important to train a diverse group of samples because the computer algorithms interpret the images very literally. I found it necessary to leave a little bit of a buffer, as you can see on the image in the middle, between the vehicle and the background to provide a little context to the algorithm. We had to keep in mind the different spatial, spectral, and temporal aspects of the imagery, so that way we could have it to notate vehicles in all of the different settings. So the next step was to train the deep learning models. I'll go over some of the different parameters. The training tiles that we just created are run through the neural networks, and they're passed back and forth through the neural network. This is known as an epoch. The number of samples that are sent at one time is known as the batch size. And on the left image, you can see at the bottom where it's highlighted, stop when model stops improving. This was very important to the study because it helped protect against overfitting, which is common with these deep computer vision networks. Overfitting just refers to overtraining, where the model just gets too specific in what it's looking for. You can see the image in the middle, where the graph is just an output of these deep after the training is complete. The average precision score at the bottom doesn't give you a good indication of how well the model is going to perform, but these can tell you if there's an outlier, if something looks like it's too high or too low, if you've done something when training the model and it just needs to be retrained. The last step was to actually run the object detection using the deep learning tool. So we just import the final raster area and the model that we just trained, and then identify an output. The arguments were very important to the overall results, as you'll see in just a second. Padding just refers to adding pixels to the raster to help increase the accuracy. Threshold refers to how sure the model has to be about a vehicle before it places a bounding box over it. Non-maximum suppression, highlighted at the bottom there, was very important to this study because it protected against multiple polygons being placed around the same vehicle. And as you can see in the image on the left, if you don't include it, it makes the results very difficult to interpret. Here's some of the model metrics that we use to grade the different models. True positive and false positive are pretty intuitive. False negative just refers to any vehicles that were not identified by the models. Precision refers to how many bounding boxes out of the total number actually encompass a vehicle. Recall refers to how many vehicles out of the total number were actually identified by the model. F-score is an important metric because it takes into account precision and recall. If one precision or recall is much higher than the other, this is known as being imbalanced. And the F-score just takes both of those into account to keep it in mind. The 100 sample models actually performed a lot better than expected despite only having 100 samples. The ResNet 34 model was able to recall over 80% of the vehicles in the study. And the ResNet 50 model was able to recall about 75%, which was 6% lower. This seemed to be an outlier from the rest of the results, as you'll see a little bit later. The 1,000 sample models performed well, but not significantly better than the 100 sample models. They showed an increase of about 4% and 6% respectively. The ResNet 50 model showed to be the most balanced of all the models with its 84% precision rate and 86% recall rate. The 2,000 sample models were very exciting because they were the highest performing by F-score. Both the ResNet 34 and ResNet 50 models were able to recall around 93% of the vehicles in the study, with the ResNet 50 model having a much higher F-score due to a much lower number of false positives. The ResNet 50 model was very important as well because it was able to break the 90% threshold for F-score, and it was able to recall 597 of the 641 total vehicles in the scene. So this was important to include as well. This is some of the alternative analysis that was done to show you how the different parameters can affect the overall score. And it also shows you that the final model parameters that we selected for this study were actually the highest performing. So here's some of the trouble spots that we had with the study. The 100 sample models have struggled across the board, but they especially struggled with unimproved roads and also with vehicles in densely populated parking lots. Now, this was an area I tried to focus on when collecting the next 900 samples for the 1,000 sample model, and also for the 2,000 sample model as well. It showed a very good increase on the parking lot analysis after this was a focus area, but unimproved roads showed to be a struggle across the board. Even the highest performing model, the ResNet 52,000 sample model, 61% of its misses came from these unimproved or dirt roads, which there's a lot of them in Tucson. The models also struggled with roof AC units and also with objects protruding from buildings, as you can see in the image there. Roof AC units are also very popular in Tucson. Now, these two struggle areas actually showed to be struggle areas for a lot of similar studies as well, which I found. So for some of the key findings from the study, there's very little experience that was needed to create a deep learning model using Esri's ArcGIS Pro. Also, a high quality deep learning model can be produced using the software as shown by the ResNet 52000 sample models, 90% overall F-score. On the other side of the equation, a productive model can be created with just as few as 100 samples, as shown by the ResNet 34 models, 80% recall rate. Overall, the ResNet 50 models outperformed the ResNet 34 models in every sample size, apart from the ResNet 50 100 sample models recall rate. Now I'll go ahead and open it up and see if anyone has any questions about the study.